So when comparing the KSP to the Q value, the Q is larger than the KSP for the solubility of silver chromate, which tells us that we would see a precipitate. So a precipitate would be observed. Okay, so things to keep in mind when you're doing these problems. Okay, so the biggest error I see is students taking the concentrations as is and plugging them into the Q value. You have to find the concentration after mixing. Okay, so and then the other thing is making sure that you're told the two reactants. You need to write out the reaction so you can see which precipitate is the one that you're wondering will precipitate out or not. Okay, so the last part to this lesson, or looking at solubility equilibriums in general, is a concept called the common ion effect. So what this essentially is up until now, all the examples we've been looking at, they've been discussing solubilities in equilibrium in water, okay, without other ions being present necessarily. So what the common ion effect is a situation where you have a solubility equilibrium, but instead of this happening in pure water, having a solubility equilibrium with another solution already present. So for example, let's say we have barium chromate and we are adding it to a solution of silver chromate, right? So if I had chromate already present, I'm actually not going to be able to dissolve as much barium chromate as I normally would because you already have those ions present. So hence the term common ion effect. So there is an ion that is already present that you're trying to continue dissolving more in it. So the example that we're using here is, let's say we had an equilibrium happening and we're going to add barium chloride to this solution. Well, what happens is you already have barium present. So what ends up happening is you're going to have an increase in barium, which would cause a shift in the equilibrium to the left, which means you will not have as many ions being able to be within the solution. So anytime you add additional ions of the same type, I should say, they have to be in common, you end up decreasing the solubility of that particular equilibrium, just because it's now going to crystallize out more because you have added in more of that ion. So we're going to look at an example of this so you can kind of get an idea of how you would approach something like this, but it's pretty similar to what we've been doing. It's just the only difference actually is instead of starting with no product, you actually have some product that is already present. All right, so let's take a look at what we have here. So it says, what is the molar solubility? So again, we're talking about equilibrium concentration. So we want to know what is the molar solubility of lead 2 chloride, but it's not in water. Notice it's telling us that it is happening in a solution of 0.2 moles per liter of sodium chloride at SATP. So we're not dissolving lead 2 chloride in water. We're dissolving lead 2 chloride in a solution that has sodium ions already, and it has chlorine ions already. So let's start off by looking at the solubility equilibrium here. And I'll show you what the difference is here between other reactions you've been doing. So first of all, if we want to know the molar solubility, that's in other words asking us to solve for the concentration at equilibrium, which in other words would be equal to X, all right, looking at an ice table. Remember, solids are not included here. Now, normally, here's where this is going to be different. Normally, you start off with 0, 0 for your product. However, because we have a solution with a common ion, there is already chlorine present. So what that means is, yes, we will have 0 lead at the start, but actually we will have 0.2 moles per liter of chlorine to already be there. The change is still the same, right? So we're going to have x 0.2 plus 2x. So notice its equilibrium is still initial plus the change, 0.2 plus 2x. So you now have, we still have to solve for x, but the difference is instead of starting with 0, common ion effect means you have a solution that already has one of the ions present at the beginning. So when we're setting up our K expression, our KSP is going to be lead and then chlorine squared, right? We have to keep in mind we're going to add this whole expression into this equilibrium concentration. Now, in this case, the KSP is not given, right? So remember, this KSP can be found in your textbook, page 802. It's Appendix C8 at the back of your book. So let's look at it on another page here. So the KSP, if you look up that value, is 1.7 times 10 to the negative 5. And we're going to plug in our expression value. So we're going to have x, and then we're going to have 0.2 plus 2x squared, right? Now, here's a situation where if we were to factor this out, we're going to end up having an x and an x squared, right? So remember, when you're factoring this, you have to multiply this by everything here. So you will have 0.2 squared times x, and then this is going to be x squared times x. So again, whenever you have a weird factoring situation where it's not going to be easy to factor out, we're going to use the 100 rule. So this is still the same rule that we learned about before, except the only difference is instead of subtracting x, we're trying to see if the purpose is still the same. We want to see if x is so insignificant, then we can get rid of this plus 2x. So remember, you cannot remove the x from the lead because we started with nothing. But when you have an initial concentration, we can see if we can get rid of that. So it's going to be the initial concentration divided by the KSP. So in this case, it's going to be 0.2 divided by 1.7 times 10 to the negative 5. And in this case, it's way bigger than 100. It's actually almost 12,000. So therefore, the 100 rule will work for us. So that makes life a lot easier because when we go to solve for this, it's simply going to be, right? The KSP is equal to x times 0.2 squared. So when that happens, right, we can solve for x pretty easily. So our x ends up being, if you work that out, 4.2, I'm doing two significant digits here, times 10 to the 4, negative 4 moles per liter. So the molar solubility of PbCl2 in that sodium chloride solution in a 0.2 mole per liter NaCl solution is 4.2 times 10 to the negative 4 moles per liter.